Okay, next one up is VHTS, a savior for Satcom. True or false? Joe Duller from GD.
Okay, hello everybody. My name is Joe Duller. I work for General Dynamics. I'm the Director of Business Development and Strategy. First of all, I'd like to thank Profin for originating this Satcom Vision and also for supporting it. So GD has several divisions that deliver antennas. Our biggest facility for antennas is our Kilgore group, and they're out of Texas, and they're going under the brand name of Vertex. There's another group in San Jose that does more, that focuses on more precision antennas, special feed designs, and RF systems that make it more ideal supplier of HTS systems. So that's where I'm gonna that's what we're gonna talk about mostly. So let's see, where's the slide? So, it worked. Okay. So VHTS. HTS basically is utilizing now mostly Ka-band gateways and has proven itself to deliver fast, cost-effective broadband connectivity via satellite. VHTS, which is very high throughput satellite, is seen as an evolutionary step to further increase the service capacity while also reducing cost. It goes to the theme that customers want more bandwidth. Satellite has always been an alternative decision. By going to VHTS, it'll offer comparable performance to a terrestrial. So to answer the question, is VHTS a savior for Satcom? You have to think about, is the technology ready, and can VHTS be cost effective for the users? So, and now we'll talk about what VHTS provides. Basically, by going to VHTS, we're providing, we're working at higher frequencies, therefore we get wider bandwidths, and that can increase the data capacity and the data throughput. Also, with the ever-increasing use of Ka-band, QV band spectrum offers a really more available bandwidth. And also, with Ka-band systems, the user terminals and the gateway terminals are typically at Ka-band. So if you put the gateway at QV band, you can co-locate the user and the gateway beams. So today, HTS systems operate at Ka-band generally. They share the same frequency spectrum. I've listed the frequencies there that you've seen before today, basically 27.5 to 30 on the uplink. In these HTS systems, what normally dimensions this whole HTS system is the forward bandwidth. So that's what we're looking at the VHTS, is to be able to maximize that. So what we do, what we're advocating to most of our customers is to put the receive at Q-band. So basically it's at 37.5 to around 42.5. And then we use two transmit bands. One is the transmit band that's used at Ka-band, and then we also add another band that does the V-band. So basically we have two uplink paths and one downlink path. And then the VHTS user terminals will stay at Ka-band. There's really no reason to switch out. They're developed and so they're ready to go. So all we're doing in VHTS is really changing the gateway. So let's look at the advantages of VHTS. So basically we're all over this lower cost per bit. Basically there's more bandwidth capacity, so we have a wider RF bandwidth available, and also, as I mentioned, that we can co-locate the user beam and the gateway beam. And also, you know, with this added bandwidth, you can potentially use less gateways, or you can get more higher throughput to the users. So, as I've said here, is the Ka-band has about 2.5 gigahertz of bandwidth. If we add to that the V-band, as we mentioned earlier, it's another 4 gigahertz. So you total get about 6.5 gigahertz of bandwidth on the uplink, which is roughly 2.5 times. So it's a significant increase of bandwidth. And also what we're also proposing to our customers is always this idea about using an incremental type approach, is so that, you know, I want to start out here and then kind of have a grow path to increase my capacity. And one way to do that is, since we have 2 uplinks, is use the Q-band for the downlink, use the Ka-band transmit for the uplink initially, start your service, and then later, you know, add in the V-band. So that's some approach that, you know, some of our customers may look at. The difficulties is we do, as someone showed, the fades. You do have more fade at V-band and Q-band, but you still have it at Ka-band, so it's a similar mitigation effect, so it's not that big of a deal. I mean, it's the same problem as we have Ka-band. And then the ERP. So we're talking, one thing we're limited by is HPA power. As CPI mentioned, it's about 250 watts. At Ka-band, we can get 500 watts. But in addition, we have another problem, is we have 4 gigahertz of bandwidth that we need to cover with V-band. So the density, the power density is lower. So the way one way to mitigate that is go with a bigger antenna. But when you go with bigger antenna, you know, we're talking about, you know, very, very narrow beams that are also make the manufacturability of that antenna more difficult. Another thing that, you know, people sometimes don't think about, but the waveguide. If you have a, you know, K-band waveguide versus a V-band waveguide, the loss per foot it's much higher at V-band. So that's another part of our whole design, is at K-band we had to reduce those waveguide runs. Now we even have to do it more, and we've done more of that in the feed. Gateway, you know, the actual one single V-band gateway is per gateway more expensive, but as I said before, if you look at uplink bandwidth, the price per uplink bandwidth, the price is actually lower. You get 2.5 times the bandwidth, but the gateway is not 2.5 times the price. So just a picture. This is what our in the middle is the 9 meter. It's basically K-band transmit, Q-band receive, and V-band transmit. And so that's what we call a limited motion antenna geared towards GEOs. We also have a full performance one on the far right, which is geared toward more like launch supports and where you need precision over the 0 to 90 degree elevation range. On the left-hand side, you'll see a hub. We have a very large hub. We're able to put 8 HPAs in the hub, along with the converters and any other things we need. It's fully air conditioned, and we keep that distance between the HPA to the feed as short as possible. And we're even doing more steps at V-band to shorten that distance. Just to give you a picture of what a transmit radiation pattern looks at V-band, this is a 9.2 meter, and you can see that those dots, those stop at about 1 degree. So you can see we're, you know, by the time we hit 1 degree, we're way down in power. But also, you know, as it states down below, it has a 3 dB beam width of 50 millidegrees. So that means you step off 25 millidegrees, and you lose 3 dB of signal. So it needs to be pointed well. It needs to be able to point well, to find the satellite even, and then it has to mechanically be able to handle the wind loads, the thermal loads, anti-icing, and whatever else we throw at it to still maintain that shape, and focusing. Focusing is the critical thing. We need to keep the subreflector in its place. Everything needs to hold its shape over the environmental conditions. So the status, I mean, we're really far along on this. This is not a product that is theoretical. It is being delivered. And basically originated from our Ka-band antenna that we've delivered since 2005. Very successful antenna. We have hundreds of them out there. And they've been, and it's a very robust antenna. So it took us a minimal amount of changes to get it to operate at V-band. We improved the optics and the feed design so that we're accomplishing much more losses. We gained about a dB of a traditional design that we have. The antenna design and fabrication is all done. The feed is done with multiple units fully tested and a few deployed at the factory. And the first V-band antenna installation is happening now, and we're going through testing for our customer this month, and will be finished by December. So it's a real antenna, it's out there, and it's available. The order status is we have two types of antennas on order. One is the one I've been describing with K-band transmit and Q-band receive and V-band transmit. Another customer wanted to do K-band receive, K-band transmit, and V-band transmit. And that's a little bit harder to feed because we got a span from 17.7 gigahertz all the way to 51.4, which is more than an octave. So we're trying to guide our customers and saying you really don't need, the system's doesn't really need that receive band on K-band. So if you can do K-band transmit, which takes us from 27.5 to 51.4, we can stay within an octave and making the feed design a bit more straightforward. So in other parts of non-antenna things, I mean, we heard from Work Microwave, CPI, and we'll hear from Zycom. But basically the standard HPA is 250 watts. They're being delivered now. And there's, that's basically what the state of the art is of today. We are looking at higher frequency bands, higher power, in line with what Gerard said, 500 watts with about 4 gigahertz of bandwidth. The production level is, the HPAs were planned, and I'm in line with Gerard on this, so that's good, and for Q1 around 2021. So a little bit off, and so right now, what we're using is, for all our proposals and so forth, is 250 watts. The LNA is not a problem. We have about 15 have come into our factory. We've tested them. The noise figure is actually coming in better than 2.5 dB. We're seeing more like 1.5 to 2 dB, so that came in nice. And as Work Microwave explained, the QV band block converters are available from single channel. We call them domains, but anyways, from single to quad IF domains, and they're ready to go. So the parts are all there. So the key takeaways are basically the higher demand is driving this whole VHTS application. And also operators are looking for lower costs. So what we're doing is trying to standardize, as Martin explained, and also we're trying to come up with ideas to incrementally build out their ground infrastructure to help with the CapEx cost. VHTS gateways offer a more available bandwidth, so the price per bandwidth is down. So, they're currently being available, and so, there's really not an issue in that, and GD is well positioned then, along with our partners, to deliver these gateways. But so to answer the question, yes, with its lower cost, higher throughput, being able to co-locate the user beams with the gateway beams, all the other advantages, we see it's a no-brainer to go to VHTS or go to these V bands for the QV for the VHTS. And that's it.